Hello and welcome to our Expert Insight video series. I'm Chitra Sethi, Editorial Director at SAE Media Group. A popular science fiction TV show once characterized space as the final frontier, but with the launch of the James Webb Telescope, America's planned mission to Mars, and numerous other space projects in the works, companies like Aitech are developing the technology to turn science fiction into science reality. With innovations like their commercial off-the-shelf or COTS-based digital backbone, they are creating the communications infrastructure that will connect the increasing number of digital technologies necessary to make it happen. In this interview, Pratish Shah, General Manager USA at AI Tech, discusses how the digital backbone concept uses COTS computing to make these innovations a reality, and how the longer duration or deep space exploration will impact electronics design. Hi, Pratish. Thank you for joining us today.
Thank you. It's a pleasure to be here.
The space covers a wide range of orbits, but can you identify some common pain points that your customers face, regardless of how deep or long a space mission lasts?
Sure, no, happy to. Building computers that go into harsh environments always has its challenges. And, historically, before space travel and space missions became the norm, building computers that went up in airplanes and cars and vehicles had that level of ruggedness that's required. Space travel introduces a harsher environment to go into. And what's different in space isn't, things like vibration and shock, because when you launch, in a rocket, a computer, you're experiencing an intense amount of vibration and shock. But once you get into space, you now introduce radiation. Where we're shielded from radiation on Earth, in space, you're bombarded by radiation, heavy ions, and protons, for example, continuously. And these particles have an effect on computers and systems. So what customers face is when they're putting digital electronics and computers and networking switches in space, they need to know what altitude they're going up to, from low Earth orbit to geosynchronous orbit to deep space. And you experience different levels of radiation effects based on that orbit. And then how long you're going to be in space. The longer you are going to have your equipment in space, the longer time that you have being affected by these radiation particles. So based on the type of mission, we want to understand the duration as well as the altitude, and that allows us to build the electronics that mitigates against the risk of what's typically called single event effects. When a radiation particle affects a computer chip, it causes a computer chip bit to switch, which may result in an erroneous output. Single event effects, typically remedy themselves through means that are built into the computer. More intense effects are like single event latch-ups. These are permanent damage. So based on how high you go, based on how long you stay, you encounter these particles, repeatedly. And therefore, we build and design computers and systems that are withstanding all the challenges that space brings to you.
That's interesting. Now, tell us something about how and why to use COTS components in space environments.
So commercial off-the-shelf is the terminology used in the space and defense and aerospace area for a while. It's the desire to use equipment that you're used to today, instead of building something incredibly customized. When you build customized equipment, it takes a long time. It costs a lot more money. And, like every customer out there, they want everything faster and cheaper. That's a common thread for everyone. So the way to go get something into space faster and get something into space cheaper is to build, technology on commercial technology and commercial capabilities. So we build COTS-based systems that have shown and are proven to fly in space. And when customers come back to us repeatedly to want to buy single board computers, network switches, network routers, memory cards, they're buying a commercial off-the-shelf product that has already been proven to fly into space. And for the customer, what they get is they get something that's substantially faster to market and lets them get to their mission much faster, to achieve their goals, and it gets something to them substantially cheaper because they're not building some product from scratch that can take not months but actually years of time out there.
So, Pratish, we are starting to hear more about a unified infrastructure across digital technologies, the digital backbone. Can you explain a bit about how the concept is being applied to space applications?
Oh, no, happy to. So, just like here on Earth, when you look at your computer and your computer is connected to the network, and on the network you have other devices that provide information, and you take all that for granted. I mean, you don't think twice about that. In space, we're seeing a similar demand for having a connected set of systems to perform set of tasks. So the digital backbone architecture that we're introducing, for the space applications, is quite identical to that. It's a networking system, network routers with computers, on the network, storage devices on the network, and it allows applications in space to leverage a fully interconnected system to perform more complex tasks. And let me provide a for example here. So one of the more popular space applications is Earth observation. So you have satellites orbiting Earth, but soon you'll have satellites, space stations orbiting Moon, and we're all capturing pictures and imagery. And by capturing all these imagery and pictures, you're generating a lot of content that becomes very hard to bring and communicate to Earth because there's not enough bandwidth to communicate all the imagery that's captured. With the digital backbone architecture, that imagery that's captured can be stored through a network system on a satellite with a payload, and store that into a storage device, gigabytes or terabytes of storage. You can have edge computing platforms that do image processing and video processing in space. So instead of sending every bit of image, every image that's brought down, you start doing analysis and assessment. Like, this is a high quality image. This is an image that doesn't have cloud cover. Let's go send that down. And I can do all that image processing. I can do all that image storage, and I leverage a full standardized digital backbone with network routers and systems that allows me to do that and do that in the space application.
Excellent. It sounds like you're really staying on top of what this industry needs. Can you tell us about the recently launched Series 300 level of qualification for components used in lower orbits and short duration space flights?
Sure. For many years, the space industry was driven by satellites that went more into deeper space, into your geo orbits that have more intense radiation effects that they encounter. As launch costs have become more affordable, and then we watch the news all the time, and it's like every other day there's a launch taking place somewhere in the world of satellites, and it's not just one big satellite. Now we're launching dozens, 30, 40 satellites at a time. And most of these satellites find their way in what's called LEO, or low Earth orbit location. And LEO environments, encounter very different radiation profile than maybe a geo environment. What Series 300 does is it's a set of products that meet the requirements for LEO orbit satellites that don't have as much risk with respect to radiation effects, that also tend to be shorter duration missions. But from a business and a market perspective, companies launch a lot of LEO satellites because they view them as sort of disposable. They may launch hundreds of satellites to cover the Earth, and then every 3, 4, 5 years, these satellites get cycled out. And thus, what Series 300 addresses for our customers is a radiation profile that's more in line with what the LEO customer, a LEO orbit, encounters. And it also meets the cost point, because now if I'm not, putting a satellite up there for 15 or 20 years, but they have to last 3 or 4 years, I have shorter duration, less radiation, and that's where the Series 300 product profiles come in.
Speaking of lower orbits, what are some of the things you see that are going to make this new area of space successful from a market growth perspective?
Oh, that's a fun question. Like everything else in the tech world, because it's cool tech, and uh, just because you can build it doesn't mean that it makes for a successful opportunity. In the end, there has to be some demand, some business, and a need for it. So if I look at in the space area and how do we achieve a market growth that will excite us in the space domain, would be demand from us, from you, from all of us around the world. And that would be things like more communication anywhere on this planet, more imagery, better weather satellite imagery, so for more access to communication capabilities and more access to imagery and content will drive demand for more space applications, more satellites. And the benefit of doing all these things, in a space domain versus Earth domain is um, once it's up there, it's up there. It covers a great portion of the planet. When you have a communication satellite up there versus a tower here, covers a small area. So you can launch, some satellites and get greater coverage. So it becomes commercially viable in that sense. So we're seeing a lot of space growth being driven by these low Earth orbits, the low cost, greater need for equipment, greater need for uh, uh, digital technology, and that's driving a lot of our growth for our products.
Right. And on the other side, deep space exploration is seeing its own growth initiatives. What are some notable factors when building space electronics for these types of orbits that typically have much longer mission lengths?
Yeah, so when you get to what's called geosynchronous orbit, you are, getting deeper into space and even go further into lunar missions, for example, or even beyond that, as we've seen NASA and other agencies go beyond into our solar system. As we go into deep space, um, we're seeing a greater amount of demand from agencies like NASA, for example. I think we're all familiar with NASA's Artemis mission, in which they are going to be taking humans back to the moon. It's an exciting mission, and it's an opportunity, for us to put, in some kinds, humans in orbit around the moon on a permanent basis, and then as a gateway that takes humans, back into deeper space, such as Mars. So, building space electronics for those types of missions, for geosynchronous orbits, the lunar to deep space, now you're experiencing much greater radiation effects. You're away from the shield of the atmosphere. You're much further away. So, the impact of the sun, the solar flares, and how that affects and ejects particles that affect digital electronics has a greater impact. Government agencies like NASA have very strict definitions of how you build digital products, how you screen components, computer chips, and build boards, single board computers, and switches and routers. How do they withstand these strict requirements? And they have different level parts that define the requirements that are needed based on different missions. So for these deep space missions and for geo missions, NASA has what's called level one parts that define the most rigid, the highest quality, highest grade parts that allow you to provide and support digital electronics that withstand the radiation profile that you experience in much, much deeper space than you do in low Earth orbit.
It's pretty cool. One last question for you, Pratish. Where do you see the next big leap in space technologies?
I think we're living in a very exciting time right now. And to think, where we were just about 10, 15 years ago, let alone 30, 40 years ago, and where we are today. If you turn the TV on and you see launches happening, I see a continuation of space becoming an extension to where we are on Earth. And, where right now we see the novelty of going in space, and we see individuals starting to experience space travel like science fiction was just not too long ago. So we see that becoming more, prominent. We see the ability to build more permanent habitats, not only around Earth, but in the future around the moon and moving forward. And to think, we have an International Space Station that's been up there for a long time, but now commercial companies see the viability to build, commercial-based space stations. And then eventually you can think that, okay, the ability to transport individuals like you and I to go into these space stations around Earth and eventually around Moon and onwards. Slowly but surely, we see that becoming commonplace. And as that becomes commonplace, the load on companies like us for digital electronics, for, better, faster, cheaper, more reliable digital electronics. So it becomes something that's just natural, will be driven by things like commercial off-the-shelf technology. You're not going to build customized solutions for every time something has to go into space. You want to be able to just go place an order, and when you place an order, you get what you need. Whether it's power supplies, whether it's computers, whether it's storage, and to make this possible, to have humans be in space in a permanent way and in a consistent way, and to allow all of us to do that, it needs to become commonplace. And commercial off-the-shelf technology is one of the means by which we can be part of that, to make humans, the presence of humans orbiting Earth and then subsequently the moon and beyond, hopefully in our lifetime.
Yeah, a lot of exciting times and, coming up soon for Artemis and all the other missions that are going to follow. Very exciting. Well, thank you so much, Pratish, for sharing your insights with us.
Thank you very much. Thank you for your time.